Good morning, friends. Today we are going to discuss about new method, new technique of coating technology. That is chemical vapor deposition process. In the last lecture, we have discussed about the physical vapor deposition process. So, in this particular process, we are going to discuss that how we are doing the coatings, how we are doing the modification of the surface, and the difference between the physical vapor depositions and chemical vapor depositions is that in physical vapor depositions just we had made certain kind of atoms or maybe the plasma and just we had deposited those onto the substrate itself. But here in this process we are going to see that how we are making this kind of atoms or maybe plasma or any kind of gas which can react with the substrate itself and do the modification. So that is why it is called the chemical vapor depositions, because there is certain kind of chemical reactions is relate with this process. Here first we have to know what is a chemical vapor deposition means. So in chemical vapor deposition process, solid material is deposited from a vapor by a chemical reaction occurring on or in the vicinity of the normally heated substrate. So whatever I have explained already in the physical vapor deposition, just we are creating certain kind of molecules, certain kind of atoms, certain kind of plasma, and then we are depositing those onto the substrate. But in chemical vapor depositions, we are making certain kind of gases or maybe certain kind of materials which will react with the substrate itself and make the coating. So the resulting solid material is in the form of thin film powder or maybe single crystal. So we are get the modification by this technique or maybe, but by this way itself rather we can say. What are the key factors in this CVD system? So first one is the called substrate material which we are going to coat or maybe which we are going to modify. Next is the substrate temperature, that what is temperature it can sustain or maybe what is temperature I can put my substrate so that it will not change its any kind of property, means like physical property or maybe the chemical property. Next one is called the composition of reaction gas mixture. So what type of gas I'm going to use, that either I can take a single gas or maybe I can take a multiple gases too, so that they can mix together. So they can form a new material, that materials can react with the substrate and doing the coatings. And then last one is the total pressure gas flows. So suppose the growth of material with a wide range physical, tribological and chemical properties. So by doing this CVD process we can do or maybe we can change this property onto the material itself. So from this particular, as I have shown in the figure, so from this particular figure you can understand that there is a certain kind of precursors which is a reagent in a gas phase, then gas is flowing, then there is some kind of absorptions and surface reaction is taking place with the substrate itself, and then at last the film is growing onto the substrate material and the release of volatile byproduct, maybe some kind of toxic gases or maybe some kind of impurities in the form of gases. It can come off from the surface itself, so that we are getting a green material coating on the top of the surface. So here it is general idea that about the construction of the CVD system, means CVD system what are these. So here I have given the construction of a CVD system. First we have some reaction gas dispensing system. Okay, look at the diagram I have shown there here. So after when the reaction will take place, all the product through these channels or maybe through this dispensary system, because we are having certain kind of flow meter, we are having certain kind of gas bottle, then we are having sublimator, we are having the generator. Okay, we are having evaporate also. The thing is that when the mixing is takes place, if there is any humidity, it can remove those humidity. If it is having some kind of impurity, it can subtract that impurities. Not only that, it can, there is a certain kind of flow meter by which we can control the flow of that particular gases onto the substrate itself. Then at last we have a plunge it onto the substrate, or maybe onto the system. Okay, so I have shown in the diagram. So then we are into some kind of reactor, okay, as I have shown in the figure, which is including the component for defining the gas flow. So by which we can put the gas into the system, we can do the mixing of system. It is totally the automatic process. Not only that, we can control the percentage of mixing of the gases into the system, we can agitate the gases. So just like it is the head of the family. And another thing is that here we are having another exhaust system, okay, at the top, which containing a total pressure controller, vacuum pumps, scrubber, scrubber, reactant recycling system. That means what type of impurities, or maybe the what type of moistures, or maybe the what type of other means which is not required for this particular reaction, that can be taken out and that can be thrown outside by this exhaust system. Okay, now let us move forward further. Next, we are having some sequence, or maybe we are having some kind of sequence for the gas transport and the reaction process. What are those? First is the transport of the reactant by forced convection to the deposition region. So here this is our suspector. Then we are putting certain kind of vapor. That vapor is actually that the material. Then transport of the reactant by diffusion from the main gas stream through the bond layer of the vapor surface, absorption of the reactants on the vapor surface. So the things is that initially I am having one chamber in which I am putting my substrate, which is known as a vapor over there. Then I am injecting the reactive gases over there. But the problem is that reactive gases may be directly not come into the contact onto the surface, or maybe vapor. So that is why we are using certain kind of force gases, or maybe generally we are calling it as carrier gases, which will take those reactive gases with itself, and then it will come, it will do not do the reaction. And the role of the carrier gas is the to just to carry those reactive gases inside the chamber and take out from the chamber itself. So absorption process of the reactor on the vapor surface process is including chemical depositions or reactions, surface migration to attachment sites such as atomic level legend kings side incorporation, and all the surface reaction. Cleans means there is a certain kind of may be holes, or maybe food, or may be certain kind of scratches by which we can do the modification. Disruption of byproduct from the surface, transport of byproduct by diffusion through the bond layer and back to the main gas stream. Transport of byproduct by forced convection away from the deposit region. So not only that, carrier gas will help you to bring the reaction gas inside chamber. Sometimes whatever the byproduct it will be created from the sealed chamber, it will take those byproduct, means waste material, from the chamber itself. Next, we'll go for the further part. Now we are going to discuss about different types of CVD processes. But the thing is that still now several scientists has given this kind of classification based on maybe the substrate, based on maybe gas they are going to use, based on that source of energy also. So here just it is particularly, it is the things is that we are trying to give this kind of classification from our side itself. So based based on the whatever the energy we are going to use, based on whatever the substrate we are going to use, how much pressure we are going to use. So what is the source we are going to use and what is the precursors are going to use. So just to generalize the classification, just to make it simpler so that the viewer can get it easily. It is totally our principles or maybe our logics to classify this CVD technique into the different kind. What are those types? The deposition processes are classified according to following criteria. So first one is the called energy sources and activations. Okay, so look at the top. So the classification made according to energy source and activation. So a rapid thermal CVD process, in short, from RT CVD, then hot wire CVD, photo enhanced CVD, laser induced CVD, plasma enhanced CVD, high density plasma CVD. So from these particular cases, you can understood that all are coming under the CVD process, but only the energy source is different. Somewhere we are using the electron, somewhere we are using laser, somewhere we are using photo or maybe the light or maybe the somewhere we are using the thermal source over there. Then next classification we are coming to the substrate. So non-porous and porous, okay, whatever the metal we are going to do, we are going to take for doing the modification, whether these material are porous phase or maybe that is non-porous or maybe the highly dense material. Then whatever the pressure we are going to use, whether it is atmospheric pressure, then atmospheric pressure CVD or maybe the low pressure CVD or maybe the ultra high vacuum CVD. So based on pressure is applied on the process, we are dividing the CVD process into three types. Okay, then next one is called hybrid sources. Hybrid physical CVD, combustion CVD. So it is the mixture of process, means the chemical vapor deposition is also with the attached with the physical or maybe the combustion. So we are using certain kind of heat energy over there with the chemical vapor deposition process. So next is called a precursor, metallic organic CVD, aerosol assisted CVD, directed liquid injection CVD. That means whatever source material we are going to take. So based on this source material, you can divide the CVD process into different parts. Next is called types of. So now little bit we'll go into in detail about the different types of CVD. So first is called the atmospheric pressure CVD reactors, APCVD in short. So from name itself you can understand that we are maintaining the atmospheric pressure for doing this particular CVD process. The reactor designs were simple, it provided high deposition rate, typically at 400 degrees centigrade, and give films in the fall of 200, 2000 to 300 angstrom per minute range. So if our material is less than that, then substrate is less than that temperature. So you can easily do it from the normal to the 400 degrees centigrade, but it is not beyond that. Next one is called the low pressure CVD process, second one. So low pressure CVD process, or maybe in short, from itself CVD in 0.25 to 2 torr range. So this is a pressure actually. So what generally we know, one atmospheric pressure is 760 torr. So either 0.25 into atmospheric pressure. So we are getting the, so that will be the range actually in the atmospheric pressure range generally we are using. Now here operation in the surface reaction limited regime. without lowering the temperature, allow for the stacking of the vapor and higher throughput, and the typically performed in a 300 to 900 degrees centigrade range. So here the temperature varies is a little bit bigger actually. So next is the ultra high vacuum CVD. So extremely high vacuum eliminates contaminants from reaching surface. So from this particular case you can understand that we are using the vacuum pump over there, we are having some delivery rail, then we are putting the gas or maybe the plunging the gas inside, then the reaction is takes place inside, and then through this delivery layer that gas is going and it is deposited onto the substrate itself. Okay, so I have shown in the figure. So next is called aerosol assisted CVD or maybe the AACVD process. Precursors are transported to the substrate by means of a liquid or maybe the gas aerosols. Here we are not going to use any kind of gas over there, carrier gas, or there rather it is carried out by some kind of liquid or maybe the gas aerosol. So from the figure, as I have shown in the figure, here we are not going to use any kind of gases over there, carrier gas are used. So we can understand that solution of precursor we are using, then we are having some kind of atmosphere atomizer, then we are using the carrier gas. Atomizer means nothing, just it will give a high pressure to onto those liquid, so that it will come into the, it will make into the small sizes bubble form, then will make certain kind of small bubble form, then that bubble will directly come into the substrate, and then what that will deposit onto the substrate itself, and we're having some heating arrangement so that it can do the chemical reaction. If there is any heat is required, then they will make certain kind of film or maybe the coating on the top of the surface. Next is called the hot wire CVD. HW CVD afford the capability to synthesize fluorocarbon and argon silicon thin film. It overcome some of the processing constraint of having the directly heated substrate. So here we are going to use certain kind of heat, so that it why it is known as a hot wire CVD process. Let us move for the next one is called a photo enhanced CVD or maybe the InShort pH CVD process. So based on activation of the reactant in the gas or vapor phase by electromagnetic radiation, short wave ultraviolet radiation generally we are using, selective absorptions of photonic energy by the reactant molecule or atomic initiate the process. Low temperature generally 150 degree centigrade needed to form films like silicon dioxide, greatly minimize the radiation damage. So here you can see that we are using certain kind of UV lamp chamber, from where we are generating the UV source, ultrasonic source over there. So that ultrasonic source it is coming, then we are plunging some kind of carrier gases, then the carrier gases is reacting with the ultraviolet rays, then they are forming certain kind of material, then that material is going to deposit onto the substrate itself. Next is called the laser induced CVD, LCVD process. So allows local deposition of materials within the focus of the laser. LCVD allows first one step deposition of the structures with lateral dimension down to at least 1 micrometer. Three-dimensional substrate of micron sizes is possible. So from this particular figure, as I have shown there, where we can get, we have given an example of CNT, that means the carbon nanotubes. So any kind of laser source you can take over there, and then that laser source you have to put in the there is having no inlet chamber where you can use the laser source. Next one is called the direct liquid injection process. So here precursors are in the liquid form, liquid or solid dissolved in a convenient solvent liquid solution, are injected in a vaporization chambers toward the injectors, typically like a car injectors. Injectors. Then the precursors vapors are transported to the subtracting material, subtracting classical CVD process. The simple thing is that car injectors is nothing but that when the fuel is directly coming and it is injecting into the engine itself. So we are using certain kind of injector over there. So that is continuously injecting that of the oil and mixture, and the continuously the burning is takes place. The same things we are doing over there also. So we are having some kind of pressure precursor tanks where we are putting certain kind of gas pressure. So due to that gas pressure is takes place, and directly the that liquid it is going into atomization process, and maybe generally we are calling it's the atomizer. So where the liquid is going, then a high pressure of air we are giving. Due to that, that liquid is forming small bubbles, and then that small bubbles is directly coming as a vapor, and then it is depositing onto the metal surface, and then a rest of vapor it is going throughout the chamber. So the thing is that here two things are there. First, I mentioned that we are putting the material in a bubble form, and then we are using certain kind of carrier gas. So that carrier gas will carry those molecules to substrate itself. Then those molecules will react with the substrate, and a rest carrier gas will come out into the vapor form, or maybe in the form of gas formation. Next one is called the metal organic chemical vapor deposition. Based on the metal organic precursors used to produce single or polycrystalline thin flames, highly complex process for growing crystalline layers. Pressure is generally 10 to 760 torr, and this technique is prepared for the thermodynamically metastable alloys. So here generally we are using certain kind of metal precursor over there. Then we need a high energy source over there. Then the materials we are going to deposit is this. Okay, so you can see in the diagram also. But the functional group of that particular material, they will react with the substrate itself, then will release, and only the metal ions will stick with the substrate itself. Now next is the latest technology, that is called the CVI process. It is known as chemical vapor infiltration process. This is also latest technology. So what means chemical vapor infiltration is a ceramic engineering process whereby material is infiltrated infiltrate into fibers performs by the use of reactive gases at relate elevated temperature to form fiber reinforced composite. So not only that you can make the composite over there, so here you can not do the coating of particular material, you can do the coating of the particular composite too. Here earliest use of CVD was the infiltration of fibrous alumina with chromium carbide. CVI can be applied to production of carbon composite and ceramic matrix composite. A similar technique is chemical vapor deposition process. The main difference being that deposition process of CVD is not on hot bulk surface, while the deposition process of CVI is on porous substrate too. So that is a basic difference between. So let us move for the next, that is hybrid physical CVD or maybe HP CVD process. So vapor deposition process that involves both chemical deposition of precursor gas and vaporization of solid source. Main difference between the HPCVD and other CVD means it is in the heating unit both substrate and solid metal source and the heated up by a heating module. Now next one is called rapid thermal CVD. In the in short form, generally we are calling it RTCVD. So use of heating lamps or other method to rapidly heat the vapor substrate, heating only the substrate rather than gas. Chamber walls helps to reduce unwanted gas phase reaction that can lead to the particle formation. So till now we just are agitating those metal, those reacted metal, those gases. But in this particular case, just we are agitating our substrate, so that it will make itself as a reactive. So that it can react with gases and then form any kind of layer or maybe the powder or maybe the coating onto it. Now next one is called the plasma enhanced CVD process or maybe the PECVD. This is also latest technology and that these equipment are very expensive too. So LPCVD with plasma source ionized gas in a plasma supplies energy to reacting gases. Lower deposition temperature to 200 to 350 degrees centigrade and good for deposition on multi-layer films sensitive to temperature. So this is all about the plasma enhanced CVD. So next one is called the high density plasma CVD or maybe the HDPCVD. So plasma enhancer CVD with very high density plasma. So here the density of plasma is more and the RF bias on the substrate and the lower deposition temperature generally 20 to 150 degree centigrade. Much lower pressure needed, just generally 1 to 10 millitorr is required. Better quality films with a less wires. So this is the most sophisticated machine than the plasma enhanced CVD process. The next one is we are going to discuss about the combustion CVD or maybe the CCVD process. In this particular case, it is divided into the four part. So it is the ability to produce a thin film in the open atmospheric using vapor precursors or maybe inexpensive precursor in chemical in solution. So generally like a painting we are using this kind of technique over. So first one is called solution preparation. Starting precursors of materials are dissolved in a suitable aqueous or maybe the organic solvent. So here we are putting the solutions over there. So these solutions to pump, it is going in a particular nanomizer. So maybe that gun which is going to spread those material into the surface itself. Then in the meantime we are using certain kind of filter. Maybe there is some impurities, there is certain kind of humidity or maybe that there is a certain kind of water molecules that can be absorbed directly. So that material is solution in the dry form, so it will go directly to the nanomizer, and here in this particular case we are doing the atomization of that particular gas. What is that atomization or maybe atomizing gas? The solution is delivered by means of pump of to a proprietary atomizer where it is converted into the submicron droplets. Here we are giving a high force of gas. So through this gas, these solutions in the liquid form is coming into the small bubble form, and then directly through this film structure then it is giving certain kind of combustion of that particular juncture, and then that film is directly falling onto substrate and it is making the certain kind of coating over there. The next step is a coating. The metastable droplets are transported by suitable gas to a flame when where there are vaporized and combusted. The deposition. Next, coating are convert onto the this deposition. Coatings are convert onto the substrate by sweeping through the flame plasma, which causes the precursor to react the compost to form the desired material. So like this way, like welding, actually we are having the flame. Through that flame you are mm, uh, marital solution and your gases is directly coming, they are forming any material, then that flame directly we are putting onto the your substrate and we are doing the certain kind of coating. Now we are going to discuss different factors considered for the selecting suitable CVD system. So first is the reactants which are used in the process, that is factor we need to consider. Then maximum acceptance leak rate for air into the system. Then purity of the deposits and the shape of the size and shape of the substrate. And the last one is called the process economic. That means why that whole process is expensive or maybe it is cheap, and not only that what type of substrate material you are going to use, and why that reaction in between the your reactive gases and substrate material can be done or not, and what are the condition inside the chamber you are required, whether you need a small more pressure, less pressure, then what are the energy source you are going to use, maybe your material can substance. So depending upon all these things you have to choose the better CVD mechanism for your particular substrate. Now let us move for the last part. What are the advantages? So first is the uniform distribution over the large areas, no compositional gradients across substrate, no need to break vacuum for source changes, more selective area deposition because of high reactive activation energy for reaction with foreign substrate. CVD layers always follow the control of the substrate and they are conformal to the substrate itself. So this is the technology, this is all advantages for CVD process. Let us go for the disadvantages also. The first one is called the most involved safety and contaminations. That is a big problem over there, and that is it can contaminate with the source, it can contaminate with the material, it can contaminate the equipment. Hybrid and carbonyls are poisonous, especially arsine. So whatever the extract gases it is coming out, maybe that can be harmful for the environment, that can be harmful for the user, maybe the operator. Metal organic are paraphoric ignite in contact with the air. Maybe it is generally some kind of flammable gases which can directly come into the contact with the air and can ignite. High cost for compounds with sufficient purity. Then they are not possible for some materials, means there simply is no no suitable chemical reaction. It cannot do any kind of coating over there, they are generally not suited for mixture of materials. So generally sometimes we face certain kind of problems for particular composites where maybe one material is react with the reactive gases, maybe another material is not react with that reactive gases. That is the one kind of disadvantage of the CVD process. Now let us discuss the what are the applications of CVD technique. Generally we are going to use for microelectronics purpose, conductors, pass layer, passivation, layer, diffusion barrier, oxidation barrier, etc. Semiconductors, second is the semiconductors lasers of optical fibers for telecommunication. Optical fibers are produced by coating the inside of fused silica tube with oxides of silicon, germanium, boron, etc. Solar energy conservation by the utilization selectivity observe and of the thin film solar cells of the silicon and gallium arsenides and dye-sensitive of solar cells. Carbon nanotubes for advanced electronics, biological and chemical devices and detectors. For this purpose also CVD technique. Then where resistance coatings have a wide industry application, coating of titanium carbonate, titanium nitrate, aluminum or cemented carbide, cutting tool inserts or titanium carbide on steel punches, nozzles, spray wheels, etc. are used extensively. Then friction reducing coating, corrosion resistant coating like niobium, chromium, etc. Erosion resistant coating, heat resistant coating like alumina, silica, carbonate, high temperature superconductors for use in medical, power grid, high energy physics application. Some kind of decorative coating, for example, titanium nitrate, gold color on watches, whatever we are calling it a gold plating like watches. Then conductive coating for integrated circuit, interconnects, display applications, solar control, electrochromium windows, automotive windows. Then at last, let us take the summary. So this CVD technology for dielectric films has provided some insights on film deposit techniques along with film properties. The CVD process steps are very complicated due to the combination of chemical reactions and gas kinetics. The CVD is typically used to deposit dielectric metal, but can also be used for metal. It's have the ability to deposit homogeneous films and coating of a particular nanoparticles with desired properties. Have a revolutionary technology aspect. Okay, so this is about the chemical vapor deposition process. Thank you.